what I was talking about is distortionless enhancement by polarization transfer. DEPT has been replaced by DEPT. DEPT is insensitive nuclei enhancement by polarization transfer. In DEPT, sometimes you see distorted signals. That might be a problem for the readers if they have distorted signals. So DEPT does not have those distorted signals, and that is why it is known as the distortionless enhancement by polarization transfer. So it is distortionless, no distortion in the signals. Enhancement of the signals occurs. How? By polarization transfer from a more sensitive nucleus like proton to a less sensitive nucleus like carbon-13. Right? Now, DEPT is a technique which, of course, is comprised of different pulse sequences. We will not go into the details of what is the pulse sequence of DEPT experiment, but the last pulse of this experiment, this DEPT pulse sequence, is known as the theta pulse. Theta is for the angle. So any pulse sequence that is before this theta pulse, इस थीटा पल्स से पहले जो भी सीक्वेंस आप अप्लाई करते हैं, जितने भी पल्सेस देते हैं, जिस भी एंगल के देते हैं, they are all the same. Before the theta pulse, everything you do in DEPT is the same, but you can actually change the theta pulse. You can change the angle of the pulse at the very end of this pulse sequence. And that is why DEPT experiment is further divided into other experiments or other techniques, like we can have a DEPT 45 technique, we can have a DEPT 135 experiment, we can have a DEPT 90 experiment, right? So that 90, 135, or 45 is actually the angle of the last pulse, that is the theta pulse. So what is the effect of this theta pulse on CH, CH2, and CH3? This DEPT experiment is used to differentiate between CH, CH2, and CH3 and quaternary carbon. One thing you have to remember is that we do not see any signal for the quaternary carbon in DEPT experiment. The spectrum that I showed you before is known as the broadband carbon-13 spectrum. Broadband means this is the broadband spectrum. This one, right here. This is the broadband spectrum, which means that all the carbons are visible in this spectrum. But if you go for a DEPT experiment, you will never see the quaternary carbons. You will only see CH, CH2, and CH3 signals. So if you perform a DEPT experiment and you collect all the data, the difference of the broadband and the DEPT will give you the quaternary carbons. But we will go step by step and see how it happens. So what is the effect of the last theta pulse on CH, CH2, and CH3? So here we have a diagram. This shows the intensity, and here we have the theta. So you can see the angle 0, 20, 40, 60, 80, and up to 180 degrees. And we have shown these different types of carbons with different lines. So this broken line shows a CH, this broken line shows a CH2, and the solid line shows a CH3. Okay. You can see some waves here. These are the waves which appear for the magnetization vectors of CH, CH2, and CH3, right? And you can see that the wavelength of these waves is different. So the longest wavelength is for CH. You can see the longest wave is for the CH. Then the CH2 has a shorter wave, almost half of CH, and then CH3 has even shorter wavelength, right? What does it mean? What is the meaning of this wave? You see, when this magnetization vector is in front of the detector, if you remember, I told you that you see a larger signal. So the intensity is higher in the positive phase, right? As soon as it goes away, like for example, if it is here in front of the detector, when it is moving away from the detector, the signal dies out, and when it is exactly opposite to the detector, it's almost zero, and then it starts growing up when it comes back closer to the detector. It comes here and then it goes back, right? So this is how it happens, which means that the angular velocity of CH3 is higher than that of CH2, which is higher than that of CH. It means कि जो relaxation process है, that is affected by the attached protons, right? So the carbon, which has higher number of protons, actually relax faster than a carbon that has less number of protons, and you can see that from the nature of the waves here. So these waves are constant for CH, CH2, and CH3. But what happens if we give a different angle of pulse? So if we give a 45-degree theta pulse, here it is. If you remember, I had told you that the position of M0 is very important. You should be able to tell what is the position of your M0 at a particular point during the experiment, or at a particular instant where you're going to give a pulse. It's very important for you guys to remember or know the position of M0. So if you give 45-degree pulse, you can see that the wave or the line for the CH is in the positive mode. The line for the CH2 is in the positive mode, see here, and the line for CH3 is also in a positive mode. So anything above this baseline is in a positive mode. You can see the intensity is in positive, and below zero it is a negative intensity signal, right? So if you give a 45-degree pulse, that is the theta pulse, CH, CH2, and CH3, they all will have positive signals. And this experiment is known as DEPT 45. So in DEPT 45 experiment, you will see positive signals for CH, CH2, and CH3, right? What if we give a 90-degree pulse? So if you see here at 90-degree, the wave for the CH is positive. So you will see positive signals for CH, but the waves for CH2 and CH3, they are right on this baseline, which means the amplitude of the wave is zero. If the amplitude of the wave is zero, it means no signal. In DEPT experiment, if the amplitude of this wave is zero at a particular point, it means no signal. So you can see that the wave for the CH3 has zero amplitude at 90-degree, and the wave for the CH2 has zero amplitude at 90-degree. Only the CH has a positive amplitude, higher than zero, which means that in a DEPT 90 experiment or in a DEPT 90 spectrum, you will only see signals for CH. You will not see any CH2 or CH3, right? What if we go for a DEPT 135 experiment in which the last theta pulse is of 135 degrees? So you can see here that the wave for the CH is positive, the wave for the CH3 is positive, and the wave for the CH2 is negative, which means that in DEPT 135, you will see positive signals for CH, positive signals for CH2, and negative signals for CH2s. CH and CH3 will give positive signals, CH2 will give a negative signal. Negative signal means in the negative phase, below the baseline, right? And for quaternary carbons, the amplitude, the intensity does not change throughout. You would wonder why we don't see any quaternary carbons. So the quaternary carbon remains on this baseline throughout the experiment. So it's here and you don't see it. How will you interpret? So this is a molecule here, and we have the broadband, the DEPT 45, the DEPT 90, and the DEPT 135, right? So let's first count the number of carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7 carbon atoms. But because these two CH3 groups, the carbon atoms have similar environment, and that is why they are chemically as well as magnetically equivalent. So they will appear at the same chemical shift value. They will have the same chemical shift and one signal. So in total, we should see 6 signals: 1, 2, 3, 4, 5, and 6. Right, and this is the broadband spectrum. This peak here is for TMS, that is L0. And apart from this, you can see 1, 2, 3, 4, 5, and 6. This bunch belongs to the solvent, that is CdCl3. And apart from these, we have 6 signals. For your understanding, they have been labeled as 1, 2, 3, 4, 5, and 6. And here the carbon atoms are also labeled as 1 to 6. So this carbon 6 is here. You can see it here, around 172 or so 171 ppm. And then we have this carbon here, carbon number 4, that is a CH2. Then we have this carbon here, CH2. Then we have this carbon number 2, a CH. The two CH3 groups, you can see the intensity is slightly higher because these are 2 carbon atoms, the rest are 1. And then we have carbon number 5, the CH3 here, right? Now, intensity does matter, but it does not matter a lot in carbon-13 spectra, just like proton NMR spectrum. In proton NMR spectrum, you can actually calculate, you can measure the relative intensities of the peaks, and that is what we call integration. So from integration, you can have an idea of how many hydrogens are present in a particular signal. But this is not the case in carbon-13. Intensities may be higher or lower depending upon the number of carbon atoms in a particular signal, but the intensity may not be exactly twice of another signal if that signal has 2 carbon atoms, like in this case. So it's a broadband decoupled spectrum. That is why you see all peaks as singlets. So you cannot differentiate between a CH2 and a CH3 or a CH or a quaternary carbon. So to differentiate between them, we go for the DEPT experiments. So the first one is DEPT 45. Remember, DEPT 45 may not be of much significance or help for you guys, but still it is sometimes used in carbon-13 NMR spectroscopy. Let's see why it may not be very significant. So if you remember from the diagram, for a DEPT 45 spectrum, like here, we should see a positive signal for CH, a positive signal for CH2, and a positive signal for CH3. So you see here, this is the baseline. All the signals that you see here are in positive phase. And all of these signals belong to CH, CH2, and CH3. So now you cannot differentiate between these 3 carbon atoms. Although DEPT 45 does not have any quaternary carbons. So you should see 5 signals in total, because from the structure, you can see that we have only 1 quaternary carbon here, this carbon and carbon. The rest have hydrogens attached to them. So in DEPT 45, you should see 5 signals. So 1, 2, 3, 4, and 5. In the broadband spectrum, we saw 6 signals. 1, 2, 3, 4, 5, and 6. One of them is missing. Which one is missing? This one. This one appearing at around 171 ppm. This is missing in DEPT 45, which means that this signal at 171 belongs to a quaternary carbon. So this is a quaternary carbon. Rest of the 5 signals from the carbon atoms, these carbons have hydrogens attached to them, either 1, 2, or 3 hydrogens attached to them. But from DEPT 45, we cannot differentiate between CH, CH2, or CH3, but we can identify the quaternary carbons. The first information that you got from DEPT experiment is that we have only one quaternary carbon in this molecule, and that can be confirmed from its structure, and that quaternary carbon appears at 171, and this 171 ppm belongs to the region where you can see carbonyl groups, and this is a carbonyl group, of course, so that is confirmed. Now, how to differentiate between the rest of the carbon atoms? For that, we go for DEPT 90 and DEPT 135 experiments. So for DEPT 90, you should see only CH signals. You see, in DEPT 90, the CH is in positive mode, CH2 and CH3, the amplitude is 0. So in DEPT 90, you should see only CH. From the structure, you can see we have only one CH. So you should see only one signal, and that is this one. So we don't see any other signal in DEPT 90, which means we have only one signal. And this signal, if you go down, it is right above this one. And you have to compare this signal with the broadband, actually. So if you go down, you stack these spectra one above each other, and you go down here, you see that it is right above this one. So this signal at around 25 ppm, which is labeled as 2, should belong to the CH, and it is confirmed from this structure here, right? So we have one CH. So we had 5 protonated carbons, or carbons having hydrogens attached to them. Out of these 5, 1 is a CH. Now we have to differentiate between CH2 and CH3. So 1, 2, 3, 4 carbon atoms are left. So we go for DEPT 135, and in DEPT 135, you can see that we have positive signals for CH and CH3, and we have negative signals for CH2. So let's see. You can see here in DEPT 135, we have 1, 2, 3, 4, 5 signals. So we should have 5 carbons with hydrogens. 1, 2, 3, 4, and these 2 will have one signal. So 4. 1, 2, 3, 4, and 5. Right? So we have 5 signals here. And you can see that 3 of these signals are in positive phase and 2 are in negative phase. And negative signals belong to the CH2. Remember, we have to differentiate between the CH3 and the CH2 here. We have already identified a CH, but now we have to differentiate between CH2 and CH3. So you know that in DEPT 135, CH2 will give a negative signal. So these 2 signals belong to the CH2 group. So if you go down and compare it with the broadband, this signal labeled as 3 belongs to the CH2, confirmed from here. And this signal, if you go down and compare it with the broadband, this belongs to 4. So we have another CH2 here, confirmed, right? So we have 2 CH2 groups, and then we have 3 signals here. These 3 signals belong to CH and CH3. We have already identified a CH. This one is a CH here. So we are left behind with 2 signals. So you should have 2 types of CH3 groups in the molecule. So you can see a CH3 here. And these 2 CH3 groups, they have the same chemical shift value. So they will give you 1 signal. So in fact, we have 3 CH3 groups, but we see them as 2 signals. And so these 2 signals right to the extreme right of the spectrum, 1 and 5, they belong to the CH3 groups. And this one, the third one, belongs to the CH. The 4th and the 5th belongs to the CH2. And the last one belongs to the quaternary carbon. And if you remember, I told you that intensity is not an issue. It is an issue in carbon-13, because you can see here these 2 signals belong to CH3 groups. Now this signal, the second signal, belongs to 2 CH3 groups. This one. So it should be twice in intensity as the first one, but it isn't. So you can see it here in the broadband that it is almost twice as the intensity of 5, but in depth 135, and they appear almost with almost the same intensity, and same goes for depth 135. So you should not be very serious about intensities in carbon-13 spectrum, but you can take them seriously in proton NMR spectroscopy. All right. So this is how you can read and interpret depth 135. So now you know how many CH3, CH2, CHs, and quaternary carbons you have in this molecule. Let's see another example here. So again, we have this broadband, the depth 45, depth 90, and depth 135, right? And we have this molecule here. So you can count the number of carbon atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. You should see 20 signals, right? So you can count here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and some might be mixed here or overlapped here, so that is why we don't see all the 20 carbon atoms. And this is the broadband. So in broadband, you should see all of these carbon atoms. Some are quaternary carbons, others may have 1, 2, or 3 hydrogens attached to them. So we go for the depth experiments to differentiate between them. And the best way to do it is to go for depth 90 and depth 135. So I will show you in this example how you can ignore depth 45. तो सबसे पहले हम क्या देखते हैं, depth 135 देख लेते हैं. So how many signals can you see? 1, 2, 3, 4, 5, 6, 7. So you should have 7 CH2 groups in the molecule. Let's see if we have 7. 1, 2, 3, 4, 5, 6, 7, and 8. तो एक जो मैंने आपको पहले बताया कि ओवरलैप होगा कहीं पर. So here maybe or here they might be overlapped. All of these signals belong to the CH2 groups. So आप क्या करें कि इनको नीचे compare करें with the broadband. So this signal belongs to the CH2, and this signal here, this belongs to the CH2, and this signal here, this one here, belongs to the CH2, and these two signals right here and here, they belong to the CH2, and these two signals, right, the one in higher with higher intensity and this one, these two belong to the CH2 groups, right? अब आपने जो ऊपर वाले सिग्नल हैं CH और CH3, इनमें डिफरेंशिएट करना है कि CH3 कौन से हैं और CH कौन से हैं. तो उसके लिए आप क्या करें, डेप्थ 90 पे जाएं. तो डेप्थ 90 में आप देख सकते हैं 1, 2, 3, 4, 5 सिग्नल्स हैं आपके पास. तो 5 CH हैं आपके पास. चेक करें 1, 2, 3, 4, and 5. So we have these 5 CHs. So we have these 5 signals for the CH carbons. And if you go down and compare them with the broadband, so this signal to the right belongs to the CH, and this one belongs to the CH, this one belongs to CH, these two belong to the CH groups, right? These 5 signals in the depth 135, they belong to the CHs because the same signals appear in depth 90 as well. So the rest of the 2 here in depth 135, they should be CH3. So these 2 signals here, to the extreme right of the spectrum, they belong to the CH3 groups. All right. So now you have differentiated between or identified CH, CH2, and CH3. What about quaternary carbons? So you can actually take a difference of the depth 135 and the broadband to identify the quaternary carbons. You see in depth 135, you see all the carbon atoms that have hydrogens attached to them, CH, CH2, and CH3. Not in depth 90. In depth 90, you only have CH, but in depth 135, you have all the carbon atoms that have hydrogens attached to them. And so to differentiate them between, to differentiate them from quaternary carbons, you go to the broadband spectrum, and you see which peaks are missing in 135. So this peak of the broadband This is missing here in depth 135, so this should be a quaternary carbon. Here in this region, we have two signals, but in depth 135, we have one. So this, the right one belongs to the CH, the left one belongs to the quaternary carbon. This peak here is missing in depth 135, so this is also quaternary carbon. This is present, of course. This is also present. This one is also present, and these two are also present. These two signals, they are also present. This signal here is absent, right? So this is a quaternary carbon. Then these two signals, they are present. Yes, this CH2 is present, this CH2 is present, and these two CH3. So we should have 4 quaternary carbons: 1, 2, 3, and 4. Let's see. 1, 2, 3, 4, and 5. We have 5 quaternary carbons. All right. So where is the fifth one? Where is the fifth one? 1, 2, 3, and 4. So let's see which one is missing. This one belongs to 160, 170, or 180. This should be the quaternary carbon of the carbonyl, this one here. And this one belongs to, it appears at around 150 or 145. So this should be the quaternary carbon of the olefin. Do we have an olefin? Yes. So whether this is this one or this one of these two, okay, this one. And then we have this one here. So this should be an olefinic quaternary carbon as well. It belongs to, it appears at around 130. So again, it is one of these two. So, but I think this is 130. This one is 130, and this one is about 150, right? And then we have this quaternary carbon appearing around 40. So it should be one of these two, but most probably it should be this one. And one of the quaternary carbons here, this is hidden somewhere. It might be hidden here behind these signals somewhere, or maybe behind this solvent signal. It might be hidden here. So you have to be very vigilant. So this is how. अब देखिए मैंने depth 45 touch भी नहीं किया, but still we have differentiated between all the different types of carbon atoms, right? And still, if you want to go for depth 45, so you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All the signals that are present in depth 135 are present in depth 45. Compare करें. This one is present. This is present. This is common between these two. These two are common. These two are common. These two are present. And these three are present here. And this one is also present. So all the signals in depth 135 are also present in depth 45. Problem with the depth 45 is that you cannot differentiate between CH, CH2, or CH3. You can only identify quaternary carbons, because you see that this signal is missing in 45 as well. This signal here is missing in 45. This is missing in 45, and this is also missing in 45. But you cannot differentiate between the rest. So there's no need to do it, because that will waste some time, money, energy, and so you can avoid it, still have the same results, right? So this was all about depth experiment. Thank you so much.